Hi everyone, my name is Katie Auchettl. I'm from the University of Melbourne. I actually did my undergrad and PhD here at Monash, so it's always very nice to come back. I'm so excited to be able to talk to you about tidal disruption events. And Eugenie gave me the impossible task of trying to cover optical, UV, X-ray, host galaxy properties of all TDEs. So we have a lot of slides. We're not going to probably get through them, but I will make sure that they're all available for you so that you can refer to them separately. And I've tried to make it a little bit modular in terms of how the lectures are set up. So we're kind of going, why is this important? Why do we study them? What are the properties? How do we detect them? And then kind of stepping through like what do we know about them at the moment? I tried to be as comprehensive as possible. I know there are some people in the room that have published on this that probably, I may have missed something and apologize for that, but it's trying to, it's hard to cover everything in a very short period. We could have actually done a whole school on it actually, on just the observational properties. So what we're going to do, so like I said, we'll start off with lectures and then we'll have a tutorial. I'll get you to play actually with some data and you'll actually get to reduce some fit some black body spectrum to some light curves. You'll actually even get to play with some spectra to fit some lines as well. So then you'll essentially be able to do everything I do and you'll be able to, essentially lead the field from now. Okay, so like I said, I'm trying to talk about the observational signatures and the diversity of tidal disruption events. I know Eugenie had the comment on his slide that if it quacks like a TDE, it is a thing. Well, I'll show you at the end that actually if it quacks like a TDE, it might not be a TDE. But I will try to present as comprehensive picture as we can possibly do. So let's get started. So when we look out into the universe, what do we actually usually see? So, well, the best indication of what is actually out there is actually given to us by the Hubble Space Telescope. And so this image here that you can see up on all the screens is actually called the Hubble Deep Field. And it's actually one of my favorite images because it actually shows that our universe contains not only our own Milky Way, but many hundreds of thousands of galaxies. And so here you can see little fuzzy objects, right? And all these things are actually little galaxies. And some of these galaxies are very nearby to us, which means that they're like millions of light years away. And some of them are actually very, very far from us. And so this image alone has been a scientific treasure trove. And so in particular, if we zoom in, we find that there are actually elliptical galaxies like this called ESO 325 G004. Of course, astronomers are not always unique when we come to naming things. And you can see that these elliptical galaxies are kind of like three-dimensional blobs of stars, and we think they're actually formed by galaxies that merge together into this larger galaxy. And then we have other galaxies that look like this beautiful one here, which we call spiral galaxies. And these are kind of the ones that you're maybe actually more familiar of. And so these spiral galaxies make up about 60% of known galaxies in our today's universe. And we know that the Milky Way, for example, is one of these beautiful galaxies. And so this one that I'm showing up here is called the Fireworks Galaxy, or M101. And this is actually famous because just in May last year, it actually had a supernova go off, and it was the closest supernova in the last decade. And so why are they called spirals? Well, maybe you can guess by looking at the picture. They're called spiral because they have this beautiful spiral structure that essentially extends from the center. And these spiral arms are actually sites of ongoing star formation and are actually brighter than the surrounding disk because all those beautiful white lights, all that you kind of see, and they're actually very young stars that are being born and living their lives. And that in the end, they'll actually go off as a supernova explosion. However, let's go back to this image. For me, what the most amazing aspect of this image is that all these galaxies that you see in this image, nearly all of them, or if not all, actually host a supermassive black hole at the center of the galaxy. And these black holes have masses from hundreds of thousands to 10 billion times the mass of our own sun. But what's even more amazing to me is that even though these galaxies are very far away, we can actually probe the properties of the black hole sitting at the heart of these galaxies. But before we get into that, why would we actually care about black holes, right? Especially supermassive black holes at the center of our galaxy. Well, for black holes, much like the one in the heart of our own Milky Way, it's been shown that the mass and sizes of galaxies is actually closely correlated with the masses of supermassive black holes at the center of the galaxy. And so what this actually suggests is that black holes must influence the growth of galaxies that they reside in, and that the largest of these massive objects objects will be associated with the largest galaxies that we observe. In addition, due to their extreme nature, because black holes are very extreme, they're some of the most extreme objects in our universe, they also provide us with kind of a unique insight into various processes that are actually inaccessible to us here on Earth. And so that includes accretion of material under very extreme conditions, formation and evolution of jets, while they can also accelerate particles up to incredibly high energies and under very extreme conditions. And so, this one particular phenomenon can provide us insight into a whole range of interesting physics that then we can actually try to probe. But you're probably wondering, like I said to you that everything has a black hole, right? Well, how do we know that these galaxies actually host a black hole at the heart of them, right? And how do we actually detect them, these black holes, in galaxies that are actually much further away than, say, our own Milky Way? Well, the most direct evidence for the existence of these massive objects actually comes from the detection of something called an active galactic nuclei, or an AGN, is something that you may have heard of before. And these objects actually have lots of material falling onto that black hole, and as it is devoured, it produces an enormous amount of energy, right? And the way that we detect these objects is actually via extreme changes in their brightness in multiple wavelengths over days, weeks, and even years. And so here, for example, I've plotted a diagram. I know it's a bit hard to see, but you should have access to the slides soon. I plotted a diagram essentially of brightness of the center of that galaxy as a function of time in different wavelengths. And what you can see is that in all these different wavelengths, from gamma to X-ray to UV and optical, and even radio, which Adele will talk about, and I completely avoided radio so that I don't take Adele's shine, you find that they has significant changes in their brightness over many years, or even over shorter timescales. It can be on a few days to weeks as well. And so so this very highly variable multi-wavelength emission suggests that there must be something causing significant changes at the heart of this galaxy. And a black hole devouring material is exactly the type of source that you would expect to produce these extreme changes that you actually see. And so apart from that, right, we also see another signature for black holes is essentially these beautiful extended outflows, or jets, like this seen in this beautiful image here. And they can extend for many light years across. They can be very large, they can be very compact, and they can only be produced if they arise from a black hole that is ejecting a lot of energy or material in kind of a very collimated way. And what you find is that it interacts with the material surrounding the galaxy and also surrounding the black hole to produce these beautiful structures as well. And so these signatures, this highly variable nature, these outflows, and even that concentration of very bright blue emission that you see at the heart of that galaxy, right, that, which implies that there must be something very hot, very actively eating, does suggest that this is a black hole. So black holes, if you think of it, kind of like a very excited toddler who wants to tell the world how much they're enjoying their meals, right? And these black holes are exactly the same, right? They're very easy to see when you look out into the sky from here. However, what we find is that it's been shown observationally that most of active black holes that we detect are actually located at a redshift of 2. They're not nearby to us, right? And so while at closer redshifts, the number of these active black holes actually just starts to begin dramatically falling off, shown here by essentially the green line that you find here. But as we know, or expect that black holes are found at the heart of nearly all galaxies, when we go out and calculate the number of galaxies that we expect that should harbour a black hole, we find that the number of active black holes don't match the number of supermassive black holes that we actually expect. However, models of black hole evolution suggest that there actually should exist a large number of quiescent supermassive black holes in which gas accretion actually occurs at a significantly slower rate. And as such, this population of quiescent or non-active black holes may be actually be able to explain the discrepancy in our observations. And so a question that should maybe hopefully will come to your mind now is that if these quiescent black holes are a non-negligible fraction of the black hole population, then how does one go and detect these black holes in these quiescent galaxies if they don't show the same properties of those of their more active cousins? Well, this is where tidal disruption events can come into this. There are other ways to do this, but of course this is a workshop on tidal disruption events, so I'm kind of just cutting to this chase. So a more direct way in which we can probe the properties of or the existence of a quiescent or non-actively accreting black hole at the center of a galaxy is by using something called a tidal disruption event. And so a tidal disruption event occurs when a star that is orbiting around a massive black hole gets so close to the black hole such that the gravitational forces of the black hole actually become so large that it actually rips the star apart, right? And this is what's trying to be shown essentially in this little diagram. And so when this happens, what we see is that what we expect is that half of the now destroyed star will continue on the original orbit of the star going around, while the other half will be gravitationally bound to the black hole, forming an accretion disk, which will eventually be accreted onto the black hole. And so you might note at the bottom, I've put here that the rates of these events are quite rare. So there's one in every 10th, we expect them to occur 1 in every 10,000 galaxies. So there's a reason why we have to look at so many galaxies, which I'll touch a little bit on later. So it's just how many galaxies you see, right? So per year, I think we expect 10 to the negative 5 per year, right, per 10,000 galaxies. So what that implies is that you actually have to look out over a large range of the sky to be able to do, and this is actually what we do. And I'll actually touch a little bit on that a bit later. So of course, we have this beautiful cartoon image, but I have to show you this beautiful simulation, right, where we can actually see the star being disrupted, parts of the material that are now being thrown out into the environment, which won't necessarily accrete onto the black hole. And as we zoom in, you'll notice that some of that material that was gravitationally bound is now being kind of accreted into you're starting to form an accretion disk, right? Which then will be actively accreted onto the black hole. And when you ever get anything that is actively accreting onto a black hole, what you get is essentially change in brightness, right? Or change in luminosity. And that is what we're looking for. And so why are these really exciting from the perspective of, say, accreting material is that, remember, they're not like their more active cousins. So if you're an AGN, you already have material around you that is accreting. But in a quiet or quiescent black hole that is not actively accreting, what a tidal disruption event actually allows us to watch an accretion disk form in real time, right? Because essentially it was nothing, and then suddenly now it's slowly eating. And so it gives us a whole different perspective of how accretion disks form around these extreme objects, apart from being very exciting objects to be able to simulate and be able to produce there. And so when does a tidal disruption event actually occur? So in particular, during the close interaction between a supermassive black hole of, say, of a mass of MBH and a stellar object of a mass and radius of M star or R star, the tidal forces exerted by the supermassive black hole, which is defined actually by the equation that is highlighted in this in the pink box on this plot, that actually is where you may actually overcome the star's self-gravity and actually tear it apart for orbits that are characterized by a periastron smaller than the tidal radius. And so what does periastron here? So this is what is defined by this RP in this diagram. Well, periastron just means the point nearest to the star or nearest to the black hole in the path of the body orbiting that black hole, right? So it's just the closest part of approach essentially to your black hole. And so the ratio of this tidal radius, this RT that is showing on this diagram, and this periastron distance, the RP that we actually have, is actually called the impact factor. And when it is much greater than 1, what you actually find is that the whole star is disrupted. When you find that it's less than 1 or around 1, actually you're starting to just, the black hole starts to nibble the star instead of completely disrupting it. And so as the Schwarzschild radius of a black hole, which is essentially the radius of which no light or other radiation can escape the black hole, is actually proportional to the masses of the black hole, the tidal radius, what we find is that the tidal radius will actually reside within the Schwarzschild radius for black holes with masses greater than about 10 to the 8 solar masses. And so as a consequence, no TDEs will actually be observable for black holes that have masses greater than 10 to the 8 thing, and because the star is a solid hole, you may be able to kind of force a little bit higher if the black hole is rapidly rotating, but most tidal disruption events that we're looking at probe black hole masses that are less than 10 to the 8, right? And usually the ones that I'm going to talk about in particular are somewhere between about 10 to the 5 to about 10 to the 7, 10 to the 7.5. Right, so they give us kind of a nice insight in not to the most largest ones, but into kind of this, intermediate supermassive black hole thing, right? So they're kind of in this nice part. And so when we detect an emission from a tidal disruption event, what one finds is that this emission usually peaks in the optical, UV, or even the soft X-rays for some parts, for some events, but most of them occur in this optical UV band. And ground-based optical surveys, such as the all-sky automated surveys for supernovae or assassin, Zwicky Transient Factory or ZTF, or the Asteroid Terrestrial Impact Last Alert System, Atlas, I think I got that correct, and many others have actually dramatically helped us in detecting and characterizing the properties of these unique events, right, because they peak in this optical UV band. While high spatial and spectral resolution X-ray instruments have actually allowed us to probe kind of the full multi-wavelength picture or emission of these events, which of course we can also tie with radio, which Adele will talk about a little bit later. And so because they are detected in optical, right, the easiest way that we can actually detect tidal disruption events is using optical surveys. And every night, a whole variety of telescopes are located around the world on the ground, actually monitor the sky, searching for these events, but also other extreme events such as stars exploding as supernova, active black holes doing their things, and anything else in between. And so this is what this image is trying to show. It's all the detections over the last 20, 30 years, I think, where all these little dots that we see are essentially supernova, AGN, or other transients that have been detected by various surveys over the thing. Why does it become more? As with time, it becomes more because the fact that we've actually been more efficient at being able to detect these. And so, like I said, these types of surveys are very efficient and they detect hundreds of what we call these transients every night. And these surveys actually publicly announce these discoveries, allowing us to actually be able to kind of follow them up. However, while these surveys are actually very good detecting supernova, so stars that are at the end of their life and explode, it's actually much more difficult to detect a tidal disruption event due to the fact that they're intrinsically rare, right? They only occur in once in every 10,000 galaxies. And so then the question you may have, well, what do we search for when we're trying to find these tidal disruption events? Well, the first thing that we need to know is what are the things that are not tidal disruption events, right? Yep, of course, sorry.
I guess that's a difficult question, but if you were to do a volume correction, like per volume, what would then be the frequency of TDEs compared to, say, all types of supernovae?
They're still incredibly rare. Still incredibly rare. Supernova are incredibly common, right? It's still on the order of about 10 to the -4 galaxies per year or something like this. Like the rates are really low, right? So, and the hard part is that, AGN do anything. A black hole likes to eat anything, right? And black hole AGN, for example, these active ones can also mimic things that look like TDEs. So this is kind of the big thing of us. What we're trying to do is piece together what we know, what we think from the theory, and then try to see if we can match the observations, but they are intrinsically rare. We're getting better at detecting them, and so I'll actually show how much we've actually increased over the last few years, but it gets complicated. All right, so they're very rare.
Sorry, can I just...
Yeah, of course.
So when you say 1 in 10,000 galaxies, do you mean 1 in 10,000 galaxies in a given year, 1 in 10,000 galaxies over the lifetime of our observations, which is, a couple of decades in a given year?
Yes.
Okay, so that's year?
Yeah, so usually we're looking in one every year in a given year. That's what we expect. Yeah, it is high.
And I thought it was a sort of typical massive black hole sort of had an experience in once every 10 to the 5 to the 6 years.
Yeah, but remember they're also enhanced in certain galaxies, right? So when you incorporate that, that's kind of where you get that. But yes, you expect them to be very, very rare, but because there's this enhancement in a particular type of galaxy, which I'll touch at the end, it's actually slightly larger per year thing. But yes, if you average over the whole of your observing thing, then it was actually pretty low.
When you say 10,000 galaxies, you mean 10,000 orbit non-AGN galaxies?
You just look at every type of galaxy. The problem is AGN, unless they're very active, right? Most black holes you see are just quiescent, right? But we don't know the lifetimes of actually when AGN turn on and off, or whether they spend some of their time very active and then sometimes very quiet. We don't understand that very well. So we're just looking at whatever we can see. There is a question about whether you see tidal disruption events in known AGN galaxies. So some of the events we do see a hint that they may have a very weak baby AGN hanging out, but it's a whole, we're just looking at everything, right? At the moment, we're just seeing whatever we can find.
So in principle, you could have a tidal disruption event in an AGN galaxy that happens to be dormant.
Yes, correct. Absolutely. Yes, absolutely. So there is probably a suggestion that maybe these black hole, or these, if you have a star that wanders in and kind of excites the black hole, it kind of restarts it back up again, right? So people look for, repeating events that you may occur, or there seems to be some signatures that maybe you get some low limit. You kind of you've just fed the black hole, so you've made it exciting, right? It's like having coffee in the morning or something.
So the simulation you showed assumed it was an naked black hole, but in principle, it could already be appreciative.
Yeah, correct. Yep, absolutely.
Make a difference.
Absolutely, and that has quite a lot of effects on the results, right? But the thing is, at the moment, we're just kind of, you have to keep it simple, right? We have to make, this is the assumption, but what we're finding is more and more evidence of actually maybe there is more of a continuum than one particular, our perfect picture thing. But great questions. But yeah, if anybody has any other questions at all, no? Yeah, feel free to just interrupt. It's okay, so how do we actually search for? What are we looking for when we're trying to find tidal disruption events, right? Well, like I said, the first thing we need to look at is what is not a tidal disruption event. And so as we know from before, AGN, or black holes that are very actively producing high variable changes in their brightness with time, look something like this, right? This is their type of emission. And so this is called a random walk, where you kind of see that the emission kind of, as it's eating, it fluxes up and down and around and around. And if we see this over a very long time scale, we can easily just kind of rule out that this is probably not going to be a tidal disruption event, because this has an active black hole sitting here. Doesn't mean that we can't have a tidal disruption occurring in this galaxy, but it's going to be very hard to separate it from the basic emission of the AGN itself. This is optical, yes. Yes. You can't actually detect TDs or separate TDs from AGN in X-rays. And I would also say radio too, but maybe a dull as thing, right? Optical is kind of the area that we kind of focus on. Then of course we have supernovae, right? So, or the stellar, the endpoints of stellar death, or endpoint of a stellar life. Well, supernovae tend to be located far away from the centers of their host galaxies, because usually we expect the supermassive black hole to be at the heart of the galaxy. And what we find is actually for supernova, their luminosities, at least in optical and even UV, tend to evolve very quickly, and they have quite a distinct shape that suggests it's not coming from a star being eaten by a black hole. And so these are kind of some samples of what we see for some supernova. We've got some stripped envelope supernovae, some type 2s, I think, as well. So this is kind of not what we expect as well. And so then what would we expect from a tidal disruption event when we're looking at this? Well, what we know is actually the brightness of a tidal disruption event, and how its brightness actually evolves with time depends on a number of factors. So first, how bright the emission from the tidal disruption event depends on how quickly the black hole actually devours the star itself and that it actually destroyed. And this depends on the mass of the star itself. And so for theoretical modeling has actually determined that this should decay or produce or reduce with time following a power law that has a t minus 5/3 dependence. And so what that actually means is that we would expect its light curve, so its luminosity as a function of time, after its peak brightness, so once it reaches peak brightness, to essentially drop off over very many months or even years, and essentially follow this t minus 5/3 behavior, where this t minus 5/3 that we see is actually set by a timescale in which the stellar debris returns to the pericenter after one orbit. There are variations to this, which is what I'll see, but this is the kind of the standard picture that people kind of start off with as well. But that's what we're typically looking for, this kind of rapid drop. But what about how quickly it rises to peak, right? Because usually if we're lucky enough, we can catch as it's slowly eating, right? Before it gets to the, the crescendo of its devouring the star. What about it rising, the source rising to peak maximum brightness? Well, the time it takes to actually for this brightness to reach its maximum, or the luminosity to reach its maximum brightness is actually very sensitive to the black hole mass and the properties of the star that actually is being devoured. But of course, seeing these equations, especially before morning coffee, can make it quite difficult to understand exactly what we're looking for. And as an observer, I like visual things, right? I like looking at pretty pictures. And so what would we actually expect these equations to try to look visually? Well, what we find is that if we plug in some properties of black holes and some properties of stellar properties, we find that smaller black holes actually rise much quicker to maximum brightness than the larger black holes that we're actually observing. And so what happens here when we actually increase the black hole mass? So here in this plot here, we've started off with a 0.1 million solar mass black hole. We can actually increase the black hole mass, and what we actually find is that the curve is now starting to stretch out, and the maximum brightness of the TDE emission also starts to become fainter. And so for a given star, right, there's only so much mass available to actually accrete, and as such, there's a maximum amount of light that we can actually get from that mass, right? And so if we stretch out that light curve to last a little longer, right, the peak is actually going to be then a little bit shallower. And so we can actually kind of go through this. We can continue going through the increasing the black hole mass as here, right? And so as we go up to larger and larger mass black holes, right, what we find is that the peak brightness gets lower and lower, while the emission takes longer to get to this maximum peak brightness that we actually observe. And the reason for this, why this occurs as you get to larger masses, is because as you increase the mass of the black hole, the gravity actually gets stronger. And so this means the star will actually be ripped apart at a larger distance from the black hole. And that means that the gas of the star will actually be in larger orbits around the black hole, and it will actually take longer for all that material to make it back to the black hole to be devoured, right? And so since we know what a TDE should look like in terms of the brightness, how the brightness evolves with time, so here's our kind of expectations, what we can actually do is try to search for these, right? We can actually see, do we see any signatures coming from the heart of a galaxy that doesn't have a known active AGN? Is there something that actually looks like this, right? And so, but one thing you may have noticed, or hopefully you may have noticed, and hopefully the title kind of gives it a little bit away, is that the brightness that we see for a tidal disruption event is intimately connected to the black hole mass, right? And how it eats the material. And so that's amazing for us because we can actually use these light curves to probe black hole masses, right? And as a consequence, tidal disruption events actually have the potential to determine the black hole mass distribution of our local universe, while also allow us to work out how black holes of different masses grow, whether they grow quickly and eat quickly, like the ones that we see from TDEs when we're actually forming accretion disk, or whether they tend to grow on much slower timescales. So they're actually a very powerful probe of supermassive black holes in the local universe, and in particular, supermassive black holes that are not active, right? So essentially we can understand the black holes that are in this local universe.
Is this limited to supermassive black holes, or you can extend it down to stellar mass?
So I'm going to focus only up to about 10 to the 5 here, but there are simulations. People are trying to see if you can get types of tidal disruption events in lower mass black holes. Would I say that they've actually found these? No. But theoretically, yeah, sure, why not, right?
How do you know what we're observing are not also tidal disruption events on normal stellar mass black holes? Is it again the argument you watch it in the center of galaxies?
So what stellar mass black holes are going to be harder to see, right, further away. So you're going to be limited to the local universe, or like to our Milky Way, to be able to look at this, and maybe some nearby galaxies. The thing is that I haven't looked into that. Right? I'm sure there's people do this. I also expect that it probably would be higher energy, but Ilya knows probably more than I do about this. I feel like it would be X-ray, very hard thing, and we don't have surveys that can do that as well, right? So optical is a good thing because we look at the sky all night, every night, optical survey, so it's easy to see. But
we could argue that low mass extra binaries are a kind of steady long-term tidal disruption event because you're tidal disrupting a star just very gradually. Overflows spectroscope onto a black hole. There are some extra binaries actually stellar mass black hole extra binaries are transient, right? So they do go on.
they just have a different name. Yeah, exactly. It's like a partial tidal disruption event on small scales, right? So it's a different focus.
They're in a triple system, then they could be deterred for very, very eccentric orbit.
Oh, 100%, yeah.
Or dynamic environments. By the way, one thing though that you mentioned, which is interesting. So I think you're absolutely. I agree with your point that lower mass black holes will be harder to see. But actually, if you look at this plot, right, you're saying that the smaller mass black holes will be brighter, and I think this plot is maybe hiding the fact that as far as we know, tidal disruption events are generally energy limited. So in fact, contrary to what you would assume from spreading a given amount of energy over a smaller time scale, actually more massive ones end up being brighter.
Yes. Yes, I did hide this. I was trying to more replicate. No, 100%. No, you're absolutely 100% on this. And
Perceived where the intent went.
I will show you actually a little bit later. No, this is perfect. No, right? But it's actually nice because sometimes when I'm putting these slides together, I do forget to incorporate these because I'm looking at things, and then Ilya knows how to pick this up, the most important parts that are actually important for later on, actually. So, but yeah, even though I did say, pick this out, it is important to realize that this is not, you have to incorporate other physics in here, but this is our, in a perfect world, this was what we expect, though. Okay, so I've gone through hopefully the context of why this is important, right? And what we're trying to search for, right? And what we actually find, right, is that, we've been trying to search for these signatures of these events for a long time. And what we find is that we find things that actually match what we expect, right? We find things that match this T minus 5/3 decay that we would expect from a star being eaten. But we also see variations from our expectations as well. And so, here, for example, is actually some observational data of two tidal disruption events, Assassin 18PG and Assassin 14Li. Right? And essentially what we see is that we get this rise to peak, at least for Assassin 18PG. We see this rise to the peak, and then we see this decay, right, from peak brightness. And this is this is consistent with what we expect from this T minus 5/3. And here in these plots, what we have is actually the different colors and the different separation actually correspond to different wavelengths. So those seen in the very pink colors, or the pink and blue colors, are UV observations, and they're actually taken with the Swift X-ray or Swift telescope in space, because we have an atmosphere that tries to prevent UV from coming to hit us unless we have an ozone hole, right? While the ground base happens to be the stuff down here, right? So we've got optical from green to red at the bottom here. And so, and so when we model these events, when we see this feature where we see this very smooth rise and then smooth decay that we're looking for, right, what we find is that, we model essentially this evolution. This allows us to determine the star that was actually being disrupted by the black hole, right? And also the black hole mass, right? And so for these particular two events that I've shown here, for Assassin 18PG, we find that these light curves imply that the black hole mass is about 3 × 10⁶ solar masses, while as for Assassin 14Li, unfortunately we missed the rise to peak for this event, but we get that from modeling that it's about 10⁷ solar solar masses, right? So just from the photometry alone, you can get that information. It's quite an amazing feat when you think about it. That in that picture, there's quite a lot of physics actually encoded. And so since the first, oh yeah, sorry, Ilya, please. Yep.
Genuine question. So,
Yeah.
As you said, you expect the decay to basically be a power law, which means that unfortunately, being a power law, it actually contains very little information if it really is a power law, right? Because there's no scale to it. So there's a scale of the rise time, and there is the peak luminosity, right?
Yep.
But you have at least three unknowns: the mass of the black hole, the mass of the star, and the stellar radius. Because in principle, it need not be main sequence star; it could be involved giant, for example, etc. And for example, your formula for the return time scale of the most bound projectile was actually dependent on three parameters, right? So you have, but if you really are measuring two things, the rise time and the peak luminosity, and you have three unknowns, how do you unambiguously solve for three quantities?
You can't. Yes, you absolutely can't. So you make assumptions, right? So most of the time people make the assumption that it's probably a solar mass or a main sequence star around one solar mass and a radius of the sun, right? And that kind of tricks, that kind of allows us to kind of get an estimate. But it is a problem, right? There is actually, depending on what time we get to there, I can talk about it a bit later, actually the type of stars that we can try to disrupt, which we think are actually moderately massive stars. So what does moderately massive? They're not one solar mass, but they're kind of like 1.3 solar masses. And this actually comes from looking at the ratios of nitrogen that we see and carbon that we seem to suggest that this might be the case, but it's hard. Right, so we have to make assumptions, right? But the black hole mass that we get is actually not that bad, right? Because we take independent observations, so where we can actually measure the dispersion measure. So essentially, it's all how the material's rotating around your black hole separately. And once the TD has gone away, and we find that actually it seems to be consistent, we can look at the host galaxy properties, and that seems to put it in the right ballpark. So even with the assumptions that we have, it's not a bad estimate. And considering we can't detect anything usually, this is not so bad. But yeah, you're 100% correct. It is a big failing of what we have here.
You said that you often assume also a stellar radius of about one solar.
Yeah, so similar to the sun. We're just saying, because we're saying it's main sequence, if you just assume a standard IMF, right, one solar mass of the sun is the most, so we just assume this.
Isn't it much more likely for half-dark stars that like supergiants, red supergiants, whatever?
Yeah, yes, but that actually causes the light curves to change, right? So here, of course, I'm presenting the ideal case, but they actually cause variations, and people do look for this. I don't think we have any strong evidence of that more puffed up ones do, right? But remember, they don't live as long, but
But red giants.
Yeah, but they don't look the same as main sequence stars.
But the thing is, remember, like, it's exactly what Ilya says, right? Is that we have to make assumptions to think it could absolutely be the case. We just need to work out ways of trying to solve that situation, right?
So it's basically an IMF argument why you pick something that's near one solar?
And it's simple, right? It means that your maths, those equations, simple because they're all equal to 1, and then we can just be like, oh yeah, it's a t minus 5/3, right? Remember, I'm an observer, so I want to make it as simple as possible, right? That's why, right? But also, yeah, just the fact that it's the IMF, right? Is that you expect more of these one mass solar stars. So. Okay, so since the first discovery of the confirmed discovery of a TD in 2014, right, there's actually we're very confident that it was a tidal disruption event. There've been a dramatic increase in the number of events that we actually detect and follow up because we've become better knowing what we're going to be looking for, and also our optical surveys have become much more sensitive and focused at finding these events. And so prior to 2018, we only had a handful of events like these ones here, but now there are over 100 candidates events. I think the last count was about 200 events that suggest that a star is actually being devoured by a supermassive black hole. And so with these large samples of events, we can actually, what we find is actually they exhibit a wide range of, variety of observational signatures. And so in particular, we find that some TDs emit both in the optical, UV and X-rays. And so this is a good example of this is actually what we call our canonical TD or tidal disruption event, Assassin 14 Li. It is a weird event anyway, but it's the one that everybody was like, yes, we found a tidal disruption event. And this is shown here, right? So it's detected in all the wavelengths that we expected, and it's got this kind of decay. Yes, the X-rays have some variability, right? And it is slightly shifted, but it is more consistent with what we expect. Then we have other events which do not seem to exhibit any observable X-rays, and this is actually the majority of events, and we call them veiled X-ray TDEs, or just UV optical events, and they are only observable in optical or UV, like this event here, SASN 18PG. And that's where most events fall into the category. Or in the last few years, we've actually found some events that emit only in X-rays, right? Only in hard X-rays. So the X-ray UV optical events are actually soft X-rays. Well, this is hard. So what does hard mean? Well, anything above about 5 keV, right? Or 10 keV hard, right? And so we're seeing quite a diversity in the types of emission that we see and from these events. And so naturally a question that would arise is what determines the diversity in emission properties of TDEs, right? And so a hint to the origin of this diversity actually comes from when we're trying to understand whether the bolometric or isotropic luminosities or the total power output across all wavelengths of a tidal disruption is, and determine whether they're actually consistent with what we expect from the Eddington luminosity of the black hole that is associated with the event. And so what is the Eddington luminosity? Well, the limit that we see, well, this is essentially the point at which the outward force produced by radiational pressure is equal to the gravitational attraction experienced by that fall matter. So what that actually implies is that there's a maximum luminosity an object of a mass can actually emit if you assume spherical accretion, and that I would say, I think also if the opacity is dominated by Thomson scattering. And so what we usually say is that this luminosity, or this Eddington limit, is the luminosity is about 10 to the 38 solar masses, something like, or ergs per second, and that's got a dependence on the mass. But in reality, we actually know that this limit can be violated due to non-spherical geometry or various kinds of instabilities and various things. But for now, we're just assuming that this is kind of the Eddington luminosity. And so what I've listed here as horizontal lines is essentially this Eddington luminosity for different masses, right? And what we actually find is that actually when we look at the sum of the sample of events, right, we have sources that are actually these super Eddington events, right? So they're violating that limit that we expect, right? And these actually have, because they have luminosities that are greater than what expects when you assume an Eddington limit. And these are, why do they tend to fall up there? Well, actually they exhibit strong jets, right? So jets can do whatever they like, right? They're collimated energy. So that means that they can easily violate what we're expecting. So these ones are predominantly only the ones that are these hard X-ray jetted events that we see. While the vast majority of them are actually sub-Eddington, right? So they're exactly what we expect them to be, right? They're kind of falling in this bottom part. But when we made this plot a little while ago, and this has been updated as well, which I'll show you before, what we notice is that there's a separation, right, between these events, right? In that essentially we get this kind of possible bimodality between the events, which have where some of them actually have these super Eddington luminosities and other have these sub Eddington luminosities, and that there's some gap in between them. And so naturally one wonders whether this is an observational bias of some form, because remember I said it's actually pretty hard to detect these events, or if this is actually telling us something about the physics or properties or environments of these actual events. And so one clue to the origin of this gap actually comes from plotting the X-ray to optical luminosity ratio of events, which I've shown here, right? And what we find is that we have the sub-Eddington events fall below the gap, and they have a ratio of about 1, right? Which means that they show nearly equal amounts of X-rays to optical UV emission, while our super Eddington events, so where they show only X-rays, right, they are actually have very high ratios on this plot. And so what is interesting is when you tie this together with understanding the properties of the material that is around these black holes, we find that there are actually these sub-Eddington events are actually in environments that are very highly absorbed and have large column densities around them, right? And so what that actually implies, right, is that there must be a large amount of material surrounding these events that is actually causing significant reprocessing, that a large amount of optical emission is produced in addition to their detected X-ray emission. Right, so this doesn't affect the super Eddington event because it's got a jet, and jet's like punching through things, right? So they don't care about the material around there. But these ones that don't have these strong jets, right, that can't happen. So what happens is that the hard X-rays are reprocessed into other wavelengths. And so what this result seems to suggest or predict is that there should be events that naturally populate what we call a reprocessing valley. So do the optical UV TDEs that don't produce observable X-rays, do they fall into this gap here, right? And in our sample, and we can actually plot this, and we find that actually this is the case, right? When we look at a sample of TDE events that emit only in optical UV, they actually have luminosities and densities which naturally populate this reprocessing valley, which actually suggests that the environment around a TDE actually leads to the diversity or of observational characteristics of the events in optical UV or X-rays. But of course, this is not the only way, right? Of course, material around you does affect this, right? But it's actually been shown theoretically by this nice work by Jane Dye from the University of Hong Kong, that actually this also may be an effect of whether something is observable in X-ray or X-ray only or optical UV only. Actually also depends on the viewing angle as well, combined with the fact that you're looking at material. And so events that exhibit no X-rays, what happens is that you're actually looking straight through the disk. So you're looking through the most material that you observe coming from the around the black hole, right? You have a lot of what we call column density or density around it, while those that show some X-rays in addition to their optical UV density will actually be much less as you kind of go up towards looking down the jet that's been funneled, right? You start to get dominated by more X-ray emissions. So we actually kind of think that viewing angle effects actually affect the properties of events that we're actually observing as well. Anybody have any questions before I move on to the next part? Okay, so now I showed you that you can see this diversity. They come in multiple wavelengths, right? The next question that probably comes up is how does the emission of a TDE actually evolve, right? So we know, like I said, that they emit in multiple wavelengths, and how, and so what we expect is that the emission from a TDE will decay following this simple power law, which is set by the time scale in which the stellar debris will actually eventually return to pericenter, which is essentially the point of closest approach to the star of the black hole. Assuming a Keplerian orbit, this timescale is expected to follow that T-5 that we expect here, right? So this is the theoretical expectation. However, realistically, the exact power law depends heavily on the evolution and physics within the accretion stream, the properties of the star itself, such as the stellar structure of the star being disrupted, the impact parameter of the star with the black hole itself, and many other aspects as well, right? So even though this is the standard thing that we kind of use, there are variations to this, and we can actually look at this now. And so let's have a look at some of the evolution of some events to see if it actually follow this T-5 that we expect. So here is our canonical event, Assassin 14Li that people like to put out. And what we find here, you've got this beautiful power law shown by the pink here that follows this T-5 power law decay very nicely here. But you may notice at the bottom, right, is that this plot goes longer than that time, right, that is shown here. What we find is that as we continue to follow this event, right, we begin to notice that the emission from this event in both X-rays and even optical UV started to become significantly flatter than the T-5, indicating that essentially that this emission from this event is now not consistent with what we call fallback, or this T-5 at late times, right? And so we wondered, right, whether this behavior is unique to this event itself, or whether, this is common in the population of TDEs that we actually look. And so what you can actually do is go look at lot of TDE events that we actually see and determine and quantify how the emission from these events actually look like at early times and those at late times. And so what we find when we do that is that actually find at early times, the light curves of TDEs tend to follow this, seem to be more consistent with this canonical T-5 associated with fallback, right? Which is shown kind of here by the thing, yep, perfect, by the histogram here, where most of them seem to be peaking here. While at late times, right, the emission starts to move away from that, becomes much more flatter than this T-5. And what we find is actually it's more consistent, the decay rates are actually more consistent or associated with emission arising from an accretion disk that is formed, right, at late times, right? And in particular, this is actually behavior, right? We see this behavior in all wavelengths, but it's actually strongest in the X-ray and UV wavelengths that we're actually looking at. And so what that seems to indicate is that after a specific amount of time of the stellar material falling back or the stellar debris falling back, this actually stops. And what happens is you actually find that you form a stable accretion disk that then powers that late time emission that we're observing. And so what that, like I said, this actually, these events actually provide us with a really powerful probe of accretion disk formation, right? Because we can wait for a while to be able to work out when it actually is going to occur. But, you know, here I said that at late times, right, it actually transitions to this thing, right? What actually sets this transition? Well, what we find is that the characteristic timescale for a TD is actually set by the orbital period of the most tightly bound debris, right? And so one way to kind of think of this is actually by this equation here, is that the fallback, the time it takes for fallback, is actually equal to 41 days with a dependence on the black hole mass, right? And we can actually plot this, right, to work out when does this actually occur, see if that's actually consistent. And this is what I've done, right, is that essentially here we're plotted actually when does this transition occur from being fallback dominated to more disk dominated, right? And what we find is actually all these plots that we actually hear, that this flattening of this light curve is actually consistent with that fallback time, right? And so essentially that's when it kind of transitions over to being a transitions over essentially to being a disk dominated at late time.